Hey Steel Friends, well I've been out here on campus and it seems like after last night's storms a little bit of damage happened. But as upsetting as this damage could be, we can always find the silver lining, and that is we have a good opportunity to take a look at some of our connection failure limit states. So I wanted to point out, we talked about shear tear out and bolt bearing, but I wanted to show you what that looks like. So we have a good example of shear tear out on this bleacher. So you can see this piece right here. This is shear tear out. Basically, we had one bolt that was over here, and it ripped out right out the edge because it had a very minimal, very small edge clearance. So when we're looking at our bolt limit states for shear tear out, this is what we're looking to prevent against. So looking at some sort of failure analysis is always very interesting, and we saw in those bleachers we had a little bit of shear tear out. So hopefully you noticed that the bolts had kind of tore out the side. So here's a piece of that bleacher, and we noticed that here was once a bolt, much smaller than most structural steel bolts, but it was a bolt, and we see where it's created some sort of tear out. And we can see that it's kind of a sloping force, and it's not exactly clean. It's not going to be as clean as our assumptions are going to be, but our assumptions are going to give us a way to calculate the strength for that tear out segment. So let's go ahead and develop equations for both the tear out strength and the bearing strength for bolted connections. So when we look at tear out strength, we want to draw a typical failure, and the typical failure follows a sloped path. In fact, we call this the Whitmore section. We assume that that angle kind of goes off the horizontal by about 30 degrees. This is what we expect the failure to look like. And of course, as we saw in the pictures, this failure surface is not very clean. There's going to, whenever you shear something, ideally things will start to fail on one surface and not the other. And we might have some sort of yielding, bending, combination fracture. And so we have to idealize that somehow. Now, we're going to imagine that this bolt has to hold all of the force VPN, and that bolt that's holding that is resting on the right-hand side of its bolt hole. And so that's what's creating the ripping motion. So we're going to approximate that on the right and idealize that as a failure as if we're pulling on that. And instead of going off at some sort of angle, we're going to approximate it as it's a direct horizontal rip through the material from the bolt out the edge. So if we do that, we're able to create a formula based on the shear strength for these surfaces. So I've drawn the shearing force in the material in green. All right, so like we did with block shear, we want to come up with strength of this individual shear tear out segment. So I want to classify the strength VRN. And so when we look at bolts, we're often going to have Rn, and we said Rn is just the resistance or the nominal resistance of a component. And so each bolt hole is each one component of the whole connection. To figure out what phi-Rn is in this case, we're going to have phi, and then we have to come up with Rn, the nominal resistance. Because we have failure on two shear surfaces there, we'll have to have 2 in this equation. Next, we learned that in block shear, that whenever we use the strength in shear of an element, we typically use 0.6 times F sub U. So our relationship from the max stress it can handle in shear to the max stress in tension is always that 0.6 F sub U. And then I need to multiply by the area over which that phi Rn over 2, that shear, is taking place. So that area is going to be a distance L sub c. And this is what we call the clear length, or the clear distance from the edge of the bolt hole to the edge of the plate. So if you took concrete design, or you will be taking concrete design, a lot of times we talk about the clear distance, and it's basically the clear distance from the edge to the first surface of the bolt or the bolt hole. That distance times the thickness of the plate will give us the area of the shear surface. So this is how we develop the equation. So then we're just going to take that 2, multiply it by that 0.6. So that gives us phi Rn is now going to be phi times 1.2 F sub U L sub C times T. Referencing AISC section J 3.10, we see that we have two different conditions when deformation at the bolt hole at service load is a design consideration and when it's not. For this class, we typically will consider that it is a design consideration, so the shear tear-out strength is going to be the value shown in the box. For bearing strength, we're concerned with that excessive hole deformation in our connection. So for bearing strength, we'll develop the similar equation phi Rn. So that will equal phi times some coefficient. We're going to give that coefficient the value c times the area in bearing. So this is going to be the bearing area of the bolt times F sub U. Since both tear-out failure and bearing failure are considered ultimate limit states, we use the value F sub U, and we'll also be using a value of phi equal to 0.75, which corresponds to a more severe failure limit state, that ultimate failure like we did in fracture. The value C is just a constant that comes from experimental tests. We have to define the bearing area of the bolt. So because it's just the area in which the bolt makes contact with the plate, we are going to use the diameter of the bolt, because that is the width over which it contacts the plate, times the thickness of the plate. So that becomes the bearing area in our calculation. Let's go ahead and define the constant. The constant is going to have a value of 2.4, and this corresponds to a hole elongation of approximately 1/4 inch from the experimental test. So basically, as the bearing failure starts to happen and the hole starts to elongate, elongation of about 1/4 inch corresponds to the constant used of 2.4. So that gives us a final formula for the bearing strength of phi Rn equals phi times 2.4 times the diameter of the bolt times the thickness. So the diameter of the bolt times the thickness is what's resting, the bearing area of the bolt, times F sub U. We go on to the next page in our notes. We have this graphic, and I want to use this graphic just to explain a little bit again about the clear distance. So when we look at tear-out failures, it's very important we know how to calculate the clear distance, or the clear length, from the edge of the plate to the bolt, or also means the clear distance between bolt holes. So just putting in the values that we have here, S. Remember, S is our stagger, so this is the longitudinal spacing between our bolts. And oftentimes when we have a geometry of our connection, we know what the edge distance is, L sub E. So this is going to be the distance from the edge of the member to the center line of that bolt. However, we typically don't label the clear length, L sub C, on a plan view of the connection. And so we're going to have to calculate L sub C whenever we go to check tear out. So let's go ahead and calculate what L sub C will be for the edge bolt from the edge of the plate to the edge of the hole. L sub C is going to be L sub E minus H over 2, where H is the diameter of the hole. Now remember, H is the hole diameter. This is what we drill it to be. And this is given to us in AISC table J3.3. In general, for standard size holes, H, the hole dimension, will be the diameter of the bolt plus 1/16 of an inch for bolt diameters less than 1 inch. And then for bolts that are 1 inch diameter or greater, the hole dimension will be the diameter of the bolt plus 1/8 of an inch. Now remember, if you have oversized holes or slotted holes, you really need to just go into table J3.3 and find out what the dimensions are so that you can calculate L sub C. L sub C, this clear distance, is just a geometry thing. So once you look up the properties in the table, you should be able to use the geometry of the connection to solve for L sub C. For the inside bolts, we're going to need to relate L sub C to the longitudinal spacing or the stagger of the bolts. So L sub C is going to be the distance S minus, now we have half a hole on the left-hand side and we have half a hole on the right-hand side. So that's going to give us an entire hole diameter. So that is how we calculate the clear distance between bolt holes. The rest of this page shows section J3.10 from the AISC specification. So again, I'm just underlining here the values that we will typically use for the bearing strength and the tear-out strength. Besides strength concerns, if you guys have done any kind of construction before or any kind of projects around the house, you also have to think about constructability. That's going to be like another limit state we'll need to check as we're going through these connections. So in constructability, we have some minimum and maximum edge distance requirements as well as spacing between the bolts. So the edge distance requirements might help us with that shear tear out. It basically just enforces that our holes are a certain distance away from the edge of the plate because we won't be able to drill close to the very edge of the plate because we'll end up producing connections that will definitely have shear tear out problems. Also, in terms of minimum spacing, I want you just to think about, now I have a ratchet here. It's definitely not going to do anything for a structural size steel bolt. But if we take a look at a connection where we have a bunch of bolts here and we have a bunch of bolts, I need to be concerned if my tool can't actually get inside. So if I have like another bolt, if I'm too close and these bolts are too close, I actually can't get my tools inside to tighten them. So, I'm using just my home ratchet wrench, which is not going to be anywhere near the size, but, the sockets needed for these bolts are going to be much larger. I mean, when we get to something like a 1-inch diameter bolt, you're looking at a giant socket that goes onto this nut to tighten down this connection. And so if you don't have enough spacing to the bolts surrounding it, then your socket's just going to be hitting the other bolts, and you're not actually going to be able to build the connection. So that is why we have some of the minimum spacing and edge distance requirements. In terms of the maximum spacing and edge distance requirements, that's more just from a corrosion standpoint. We don't want to have connections where metal's touching metal and they be kind of loose. and loose enough for moisture to get inside there and cause corrosion. So we have limits on, how far we're allowed to have metal touching metal over a certain distance to prevent corrosion from happening inside the member. Corrosion that you wouldn't be able to see as an engineer or an inspector. Here are the minimum, maximum edge distance and spacing limitations as given to us in the AISC specification. And again, these are primarily done to maintain clearances between the bolts and nuts in order for us to be able to insert our wrenches and sockets during construction. So if we look at the minimum spacing in sort of this paragraph where it says the distance between centers of standard, oversized, or slotted holes shall not be less than 2 2/3 times the nominal diameter D of the fastener. However, the clear distance between the bolt holes or slots shall not be less than D. So I like to turn this into a formula with some letters. So this basically tells us our distance S has to be greater than or equal to 2 2/3 times the diameter of the bolt, preferably 3 times the diameter of the bolt, and that's given in the user note. So we'll just check against 2 2/3, but if you can, provide 3 times the diameter. Additionally, we should check that the clear length is greater than or equal to the diameter of the bolt, and that's usually almost always the case, in a well-designed connection at least. All right, let's label some of these variables in the picture. So we have the edge length L sub E. So this is the distance from either edge of the plate. So it would be from the top or bottom edge to the center line of the bolts. And we're given L sub E from the right edge of the plate to the first line of bolts. And then we have our stagger S in there. Now S, the spacing needs to be any which way in the connection. So, and the clear length is the clear length between the bolts or the clear length to the edge of the plate. I've gone ahead and drawn a larger connection. Now, this one we have again the edge lengths, and I'm just going to generalize this. All of these are going to be S's, the spacing between any bolts. We also even need to consider in a staggered connection the diagonal spacing between bolts. Because again, that spacing of 2 2/3 times the diameter of the bolt is meant so we can get our tools in place. So our tools are usually circular, and so it doesn't really matter if it's, in the horizontal direction or on a diagonal, it'll still be in the way. The next paragraph talks about the minimum edge distances. Basically, the minimum edge distance L sub E in both of those connections above needs to be greater than the value given to us in AISC table J 3.4. So we'll see table J 3.4 on the next page of our notes, and we just need to make sure this edge length is greater than that value. Our last construction limitation will be the maximum spacing and edge distance. And this is really a limitation on the serviceability of the structure or the life cycle of the structure. We don't want to have surfaces that are in direct contact that moisture can get between and cause corrosion. So basically, we want to make sure our connections are sufficiently tightened together and the two plates are brought together in tight contact with all the bolts. And so basically, we have these limitations on the distance from any edge to a bolt line. So L sub E has to be less than or equal to 12 times the thickness of the thinner member, and L sub E has to be less than or equal to 6 inches. And that's just meant on the edge boundaries to prevent long distances where moisture can get between. Likewise, we have to look at it in the longitudinal direction between the bolts. So we have two different cases for painted members and unpainted members, case A and B, and the stipulations are given there for the maximum spacing. So our spacing has to be less than these values. That wraps up tear-out strength, bearing strength, and constructability concerns. So now we'll move on to look at the bolts themselves and see how much strength, especially what shear strength, these individual bolts can contribute to the system and how we account for that in the design of our connection. So I look forward to teaching that to you next.